Hello, good morning. Welcome everybody. I'm gonna get started and I'm gonna share the screen. Great. Okay. So if anyone wants to use the chat room, it's at tlk.io/PILadiesRemote. So if you have any questions, you can go ahead and ask them there. And I'm going to go ahead and wait for other people to come in, and then we will kick things off. And hopefully everyone can see that. Okay, so now we are 4 minutes past 8, so I'm going to go ahead and jump in. And if you have any questions, feel free to ask them in the chat window. Again, it's tlk.io/PILadiesRemote. And I will go ahead and kick things off. Let me make sure this is presenting. Okay, cool, looks good. All right, so my name is Amanda Sopkin, and today I'm going to be talking to you about cryptography in Python. So just a disclaimer, I am not a security expert or a lawyer, so none of this is legal advice on how to do your encryption or anything like that. This is intended for introductory purposes to give you an idea of how cryptography works in Python and a little bit about how it works in general. So it should be a fun introduction. So I'm going to start off by talking a little bit about the history of cryptography, both because I think it's interesting and also because there are some good lessons to be gained there. And then we'll talk a little bit about some of the more familiar concepts in cryptography and how those work. And then we'll dive into Python specifically. We'll talk a little bit about how to choose a language when you're looking to encrypt something. We'll talk about Python's cryptography library, some ways to jump in and get started if you're interested in contributing to that. We'll talk about a few of the more common breaches for encryption. And yeah, that's a little bit of a roadmap of what we'll be up to. And I will try to keep checking the chat window here. So if anyone has any questions, put them there. And then at the end, I'll definitely check that and go over what people have said there. Great. So if you look up cryptography in the dictionary, the definition that's written there is the art of writing or solving codes. And if you are a programmer, you might find this definition unsatisfactory because that's sort of our job title and it doesn't really give you a lot of information, just writing or solving codes. But there is a better definition out there, and that one is read as a method of storing and transmitting data in a particular form so that only those for whom it is intended can read and process it. So basically, encryption at its most fundamental level started from the idea that you want to transmit a message, you want to send it to someone, and you only want the person you're sending to be able to read it. So if you were ever a kid and you played around with like invisible ink and you would write a message to your friend in invisible ink and they would need a special kind of light to read it, that kind of comes from a similar place. You want to send a message to your friend, but you don't want anyone to be able to intercept it along the way. And you need to be able to communicate in a shared language. So yeah, that's the basis of cryptography. And we'll talk about where it started and then where it is today. So I want to start out with this comic. This little stick figure is presenting an encryption algorithm to the audience. And he's saying, my crypto system is like any Feistel cipher, except in the 5 boxes, we simply take the bit string down, flip it, and reverse it. And the caption is, "I've been barred from speaking at any major cryptography conferences ever since it became clear that all my algorithms were just thinly disguised Missy Elliott songs." So I like this because I like Missy Elliott songs, but it's also kind of an example of a more basic cryptography algorithm where you're just bit shifting and reversing particular bits to encode it in a way. So at its most basic level, a cipher is just done by applying a particular kind of transformation to some text, and then keeping that system in mind so that once you have the encrypted text, you can easily reverse that and figure out the original. Great, so now let's dive in a little to cryptography history, and I'll check the chat room again. Great. The usually accepted start of cryptography is around the time that hieroglyphics came into play, which is around 1900 BC. So not all hieroglyphics are considered cryptographic, but essentially there was one particular maker of hieroglyphics that started applying a particular slant to the hieroglyphics he was writing in order to try and make them appear a little more sophisticated. So although his intent was not to obfuscate what he was writing and make it clear to only one person, which is true encryption, it's kind of the same idea of applying a transformation to text. So that's where a lot of people pinpoint the beginning of cryptography. And this is just a list of the more common hieroglyphic forms. So if you could picture like slanting them or writing it a slightly different way so that it would have a different meaning to someone, that is considered the basis of cryptography. So, and then fast forward a long way to 100 BC, and Julius Caesar came up with one of the more well-known ciphers that you'll see referred to in literature. And basically, it's a substitution cipher, meaning you have your plain text your original text that you're starting out with, and you substitute each character, perhaps just a few, with another character. So for Caesar, he used a shift by 3. So each character is essentially shifted by 3 places. So the character A will be replaced by the character D, B is replaced by E, and then so on. And eventually it wraps around so that X gets replaced by A. So you can see how this would make the message impossible to understand at first glance, but you can maybe also understand why it's not the most secure method of encryption. If I knew that he was doing this by substituting letters, I could try a bunch of different combinations and then figure it out, particularly if I knew that there was a shift applied. Shifting by 3 is not very mathematically intense. So, and then fast forward to the 16th century, and a French diplomat named Blaise Vignier came up with another really popular cipher. It's called Vignier's system. And it's considered important historically because it's the first encryption method to use something that looks like a key that we might use in modern encryption. So basically, in one of his ciphers, the encryption key is repeated multiple times throughout the entire message, and you create the ciphertext by adding the message character with the key character modded by 26. So again, this isn't a super complicated system, but because it's using an encryption key, that makes it a lot more secure. Because now, instead of like Caesar's system just relying upon the system being unknown, it also has the added layer of security of a key. And this brings us to one of the very important principles of cryptography, which is Kirchhoff's principle. And the idea is that the secrecy or the security of your encryption system should rely upon the secrecy of the key and not the secrecy of the system. So the idea is that even if I understand the method or the algorithm that you're using to encrypt, that's okay, as long the secrecy of the system should not depend on me not knowing how that works. It should be okay for me to know it as long as I don't know the key. And that's a lot more secure because it's a lot cheaper essentially to come up with a new encryption key versus inventing a totally new algorithm or system. So this is a really important piece of cryptography. You never want to design something that is only secure so long as no one else understands how it works. It's more secure to have this idea of a key that essentially is the key to encrypting your system. So into the 19th century, we came up with one of the first mechanical cryptographic methods, essentially. And Hebern designed something called the Hebern rotor machine. And basically, it uses a single rotor, which keeps a secret key embedded in a rotating disk. And this key encodes a substitution table so that every time you press the keyboard, you get a particular output. And then this rotates the disk one notch, and then a different table is used for the next thing that you're encrypting. So it looks something like this. You can see the rotating cuff and then the key presses there. And this is eventually broken by determining the letter frequencies. So essentially, if you have a ciphertext that's just done by substituting one letter for another, then you can break it pretty easily by looking at the frequencies of the letters that appear in both the original, or sorry, in the ciphertext. So I'm going to talk through an example of how that might work. And let me check the chat room again. Oops. Cool. And everyone still see this? Okay, great. All right, so we're going to talk through the letter frequency method for breaking text that has been encrypted. So let's imagine that we start out with some text that looks like this. So it's a lot of gibberish. We can't read any of this. There's nothing that looks familiar here. So we start out, and let's say we count up the frequency that each letter appears, and we see the number. The letter A appears 5 times, the letter L appears 39, and then we sort them from the most common to the least common. So we can see here that the letter S appears the most commonly in our encoded text. It appears 88 times. Great. So then we use the standard frequencies of an English letter and apply them to a text that's about this long. And we see, oh, the letter E should appearing about this many times. The letter T should appear about this many times. And this gives us an idea of where we might make some substitutions. And then here is the frequency of the letters in the cipher. As you can see, S and O are the most common. Great, so now that we have this table that gives us the most frequent letters that are used in our cipher, we can see that S and O are the most common ones. And then we look at this graph, which tells us the most frequently used letters in the English language, and that gives us E and T. So this gives us some indication that we could make some substitutions between E and S, and then O and T. So if we substitute E for S and T for O, it still kind of looks like gibberish, but it's a good starting point. So this is what the substituted text looks like. So now we start looking more manually for things that look familiar to us. So one thing that we see right away is that we're seeing the letters T, L, E pretty frequently in this text, which looks pretty similar to the, which is a very common used word in the English language. So that gives us an indication that we could probably safely substitute the letter H for the letter L. So you can see also that this letter, this word TG is appearing pretty frequently. So we can guess that because G is appearing frequently, it must be either the letter A, I, or O. And we see right here towards the beginning, there's TG. So it makes the most sense for that to be 2. So we can probably substitute O for the letter G. Great, so now we've gone through and applied that substitution. So you can see a bunch of instances of the word to, and then several of the word the as well. And now we kind of follow the same process to look for words that seem familiar and potentially make substitutions and then see where that gets us. So we've got the letter, we've got OFE, which looks pretty similar to 1. So we're thinking maybe we could substitute the letter N for F. And then here we've got THEF. So that gives us another indication that we can substitute the letter N for F, because then we'll get the word then. And here we see LHEET, so we could potentially substitute S for L, and that will give us a word that we recognize. Great, so we've gone ahead and done that, and you can see that you're starting to see more things that resemble real letters. For example, we've got so on in here, we've got the, so we continue the same process. This one looks a lot like solve, which tells us that we could probably substitute L for D, and then we can probably keep V as the letter V. And then we see OK here, so we can potentially substitute the letter N there or something else. Great, so we do those substitutions. So we substitute the letter R for K, so now we have a lot of ORs instead of OKs. And we've encoded or decoded this letter solve here. And you can see this is starting to look more and more like English. There's more recognizable. For example, we can see letter is in here a few times, solve is repeated. We see the word enough, which gives us another 2 characters that we can knock out. It tells us that we can probably substitute the letter U for the letter Q and the letter G for the letter R. And there's a couple more that are like that once we've decoded enough. So this looks something like message. So we can probably put M in for E and then A in for M right there. And then here we see something that looks a little bit like count. So we can potentially substitute the letter C for N and have that work here. And you can see it's starting to look more and more like text that we might recognize. So we conduct this process a few more times. You can see there's several good ones in here. For example, this looks something like occurring over here on the right on the second line. So we can potentially substitute, that's another indication we could substitute C for N and potentially I for P. So you just kind of continue in this way if you're doing this by hand and see where substitutions make sense and get closer and closer to something that resembles English. And then finally, after a few more steps, we end up with the decrypted text, which tells us sort of how to do this method. You find the most occurring symbol and you change it to a different letter. And this whole time you can rely upon that same graph and see, okay, this is a pretty common letter in the English language. Does it make sense to change this ciphered letter to this letter? So that gives you an indication of how a system like Keyburns could be broken pretty easily by looking at the letter frequencies. Basically, it's relying upon this input, and it's got this rotating cuff, which is the key, and then it defines a particular set of substitutions that can be used to encode something. Great, and let me check for questions. All right. Cool, let's keep going. So in World War I, we have one of the first cryptographic machines that was used for essentially warfare purposes. So this is known as the Enigma Machine. And it was invented by a German engineer named Arthur Scherbeis at the end of World War I, and it was also used heavily during the Second World War. And so this one is similar to the Keyburn machine using several different rotors, but these ones rotate at different rates. So as you're typing on the keyboard, they rotate and then they output appropriate letters of ciphertext. The key in this case would be the initial setting of the rotors. And this was eventually broken when Polish cryptographers figured out how to obtain the daily key and figure out the message decoding. Great, so let's fast forward a bunch of time to 1973, and around this time period, IBM decided that customers were going to need some form of encryption, so they formed a crypto group, which was headed by Horst Feistel, and they designed a cipher that came to be known as Lucifer. And in 1973, the National Bureau of Standards, which is now known as the National Institute of Standards and Technology, put out a request for proposals for a cipher that would become a national standard. And eventually, this one that was invented by IBM called Lucifer was accepted, and it was called the Data Encryption Standard. And just to go back really quickly, the Data Encryption Standard was eventually broken by an exhaustive search attack, so we'll get into that. But essentially, this works by trying to brute force the data encryption standard key in a matter of days. So there are attacks that work by trying to figure out the algorithm, and then there are attacks that work by trying to obtain the key. And in this case, it's sort of a brute force attack that consists of the attacker just trying a lot of different keys with the hope of eventually guessing correctly and then checking the output. And it's called an exhaustive key search. So just a note on block ciphers, it's a very popular form of encryption, and it's rather mathematically complex, but basically it's described as a pseudo-random permutation on a given space. So the other type of ciphers that you might see are called stream ciphers, which is basically just like a stream of different bits that you're encoding as they come. And instead, a block cipher, which is by far more popular, encodes a block at a time. So it's not just taking every single bit as it comes in a stream. So some of the more advanced ones will use 128-bit blocks and then rely upon a 256-bit key. And essentially they'll apply a series of mathematical transformations to that block in a way that's very difficult to do computationally and intense enough that it's not easily broken. Great. So this is a very simplistic diagram of what that might look like. You have your unencoded text, you send it through a block cipher, which has a particular key associated to it, and then you end up with your encoded text. All right, so as I said before, this data encryption standard was eventually broken by an exhaustive search attack. So in 2000, around that time period, they decided that we needed something a little bit better. So NIST put out a request for proposals, and it received 50 submissions and eventually accepted one that's pronounced rindal. The joke is that rindal, this word is pronounced AES because that's the more popular name. And this was definitely more secure than the first go around. So this is one step in the transformation. It's also a block cipher. So you can see there's some linear math happening here. And this is only one of the transformations that happen in this process. Great, so in this period of history, we were also entering into the crypto wars, which is an unofficial name for the United States government's attempts to limit the public and foreign nations' access to cryptography, essentially. So basically, the idea was that these cryptographic methods were strong enough and important enough to national intelligence that their export should be restricted. So around this time, cryptography software was included as a category 13 item into the United States munitions list. And this is a t-shirt, which is kind of jokingly referring to the crypto wars. And it says, warning, this shirt is classified as a munition and cannot be exported from the United States or shown to a foreign nation. And it's explaining something about RSA encryption and Perl. So this is a joke, but it's actually a pretty common practice to restrict the export of pieces of technology or ideas like this in order to try and prevent foreign access. So basically, the idea was that the government didn't want other foreign nations to understand how the cryptography was working, and it also wanted to have the upper hand so that potentially United States operatives could more easily decrypt foreign nations' messages than they could decrypt ours. But it didn't really work out. Basically, they put a key size restriction upon encryption, which started out at 40 bits. So back when Netscape was developing its first web browser, they put out two different versions. And the United States edition had the full 128-bit strength, but the international edition just had 40 bits. And it revealed the other 88 bits of the key in the SSL protocol. And it turned out that getting your hands on what was the more secure domestic version was sort of a big pain, essentially. You can imagine how difficult that would be to restrict access to only people living in the United States to a particular version of the browser. So as a result, most of the public, including people living in the United States, ended up with the weaker international version, and a ton of them ended up getting hacked. So this caused a lot of problems, and eventually, as a result of issues like this, and also a lot of work by open source advocates, encryption software eventually became open sourced. So in 1996, President Clinton signed the executive order 13026, which transferred commercial encryption from the munition list to the commerce control list. And it also stated that the software shall not be considered or treated as technology in the sense of export administration regulations. And it permitted the Department of Commerce to implement rules which simplify the export of proprietary and open source software. So that's sort of where the crypto wars ended. And in 1991, we have the introduction of something that's pretty important in encryption. This is pretty good privacy, which is essentially a framework that's used for most of the encryption that we do via email. And it was developed by Phil Zimmermann in 1991. So I want to talk a little bit about how PGP works. Basically, it's relying upon modular arithmetic, which uses operations that are very easy to perform, but very hard to reverse if you don't know how it was done. So essentially, it relies on having really large prime numbers. And if you have a really long, as in like thousands of digits number that's composed of two different prime numbers that are multiplied together, that's a pretty easy operation to perform to get the large number if you know the two numbers that you're starting with. But if you don't, it's extremely difficult to come up with the two primes. So you would need a supercomputer that would take a really long time to brute force the solution to that. And so the way this works, there's essentially three different keys in PGP. And essentially, you use public and private keys to securely transfer a third key from A to B that's used to encrypt and decrypt whatever information you're trying to send. So if you can picture this, if you generate a random key and then use that key to encrypt some message that you want to send that says like, hey, hello. I send you my public key, and then you use that to encrypt your random key. And then you send both the information you've encrypted, your hello message, and the encrypted random key to me. And then I use my private key to decrypt your random key, and then I use your random key to decrypt the data. So you can see how this is a little bit more secure than the methods we were talking about earlier that just have like the one encryption key. And this is a little bit of a graphic on how that works. Okay, so now we are going to talk a little bit about randomness and why it's important for the security of cryptography. So a lot of what we've talked about is emphasize the importance of having a secure key, and having something that's random to an extent is a huge piece of that. So you want something that's not easily repeatable. You do want to be able to repeat it, which means that it's pseudo-random. It's not purely random, but you want to rely upon a certain level of randomness in order to achieve something that's not easily guessed. So I want to talk about a historical example of when a weakness in a random number generator caused weakness in encryption. So there was this algorithm that was introduced in 2004 called the dual ECPRNG, which really just rolls off the tongue. And it was standardized by the National Institute of Standards and Technology in that year. Okay, so fast forward 3 years later, in August of 2007, two different Microsoft engineers found a flaw in this algorithm, and they presented the flaw at a smallish cryptography conference for Microsoft. They put out this paper called On the Possibility of a Backdoor in the NIST Dual ECPRNG. And when this paper was first released, it kind of caused some waves in cryptography circles, but it didn't really get a lot of traction. But 3 months later, Bruce Schneier published an article in Wired about these findings. And it was entitled, "Did the NSA Put a Secret Backdoor in New Encryption Standard?" So you can see that things are sort of escalating at this point. All of a sudden, it's not just, is there this mathematical weakness in this algorithm? It's being stipulated that the NSA deliberately put this weakness into the algorithm so that they would be able to figure out the output of it, which is a much bigger deal because it has severe privacy implications if the NSA is deliberately putting a backdoor into something that's used as a national standard for encryption. And in the paper, he said that this weakness would allow the NSA to determine the state of the random number generator and thereby eventually be able to read all data sent over the SSL connection. So obviously this is getting pretty problematic. This is a pretty huge deal, especially if you're considering SSL. And when you have a big national standard algorithm like this one, it could definitely be used in an SSL protocol. So for example, if I use the dual ECPRNG to generate a particular nonce that I'm sending to a Wi-Fi access point to form an SSL connection, then the NSA could predict the secret that I'm going to use to generate during the corresponding handshake to establish that Wi-Fi connection. And given that information, they could read all of everything that I'm transmitting over the wire. So obviously that has, again, severe privacy implications if the NSA did this deliberately in order to be able to interpret things that are being sent over a Wi-Fi connection. There we go. Okay, so fast forward a little bit all the way to 2013 when the Snowden papers were leaked. It turns out that one of them mentions this specific algorithm, and it says one of the purposes of Bull Run was described as being to covertly introduce weaknesses into the encryption standards followed by hardware and software developers around the world. So now we've gone from not just this being a mathematical weakness to it theoretically being done purposely in order for the NSA to be able to secretly decode the output of this algorithm, to being part of a larger system that was designed to introduce these weaknesses slowly into encryption methods. And as a result, there was this piece in the New York Times entitled "NSA Able to Foil Basic Safeguards of Privacy on Web." And they mentioned specifically this algorithm. So then shortly thereafter, the NIST recommended removal of the algorithm as a standard. And at this point, essentially since the weakness was publicized, most companies weren't using it anymore, but it took a really long time for it to be formally removed. So to go over the timeline, in 2004, the algorithm was introduced. 3 years later, those two engineers presented this flaw, and then it kind of made news later on that year when it was in Wired magazine. And then in September of 2013, when the Snowden papers were released that year, it comes out that one of the purposes of the program was specifically to introduce flaws into encryption standards. Later that year, there was a presidential advisory committee assigned to examine existing encryption methods. And then the next year, the standard was removed. So in total, it was around for about 10 years since it was first invented until it was finally removed as a standard. And that kind of did a lot of damage on a technical level. You can go on the NIST website and look up how many pieces of technology were affected by this weakness. And it's essentially any company that you can think of. And this kind of makes sense if you work in technology. It's like if you're using a particular library that has a problem and then another library uses that library, and then Microsoft puts that into one of its pieces of software, and then maybe F5 Networks is using that. These things can spiral pretty easily. So it ended up being a pretty big hit for the technology industry in general. Great. So now I want to talk a little bit about some of the ways that we use cryptography every day, potentially without really noticing it. So when you're connecting to Wi-Fi, you're going to go through sort of a handshake procedure as you're connecting to the access point. And in the process, you're going to use something called cipher blockchaining message authentication code protocol, which is CCMP for short. So basically, if I want to connect to my Wi-Fi, my computer, gets up and running, and it sends a random nonce to the access point. And then the access point receives that and decrypts it and sends its own Wi-Fi nonce back. And then I receive that, and we sort of continue sending these messages back and forth and maintain a connection. And it's important to not be able to transmit that in plain text, because obviously if you knew every single time that I was going to be sending the number 123, then you could easily intercept that connection. And this is very similar to how a lot of the operations that we do every single day works. So if you're logging into Facebook, if you're sending encrypted email, if you're doing online shopping, if you're Skyping or using this Google Hangouts call, a lot of those rely upon that same concept of having that secure handshake where you're transmitting an encrypted message. Great. So now that we've talked a little bit about the history of cryptography, let me make sure there are no questions. Awesome. Great. Yeah. So now that we've gone a little bit over the history and everything, I want to talk about specifically what makes Python suitable for cryptography. So there are some things that make this language really good for cryptography applications. It's very accessible. It's really easy to read. It's fast enough for most purposes that you would need. If you're going to be creating random numbers for an SSL protocol or something like that, you're going to need a lot more server power, and you're probably going to need to use C. But Python is fast enough for most things that we would want to do. And it's also very well documented. The cryptography module is pretty easy to understand, and it's pretty accessible and well documented. There are a few cons of Python, some things that would cause people to say it's not the most secure language that you could use for cryptography. It is dynamically typed, and generally statically typed languages are considered a little bit more secure when it comes to cryptographic applications. And essentially that's because there are some static analysis things that you can use to make sure that a particular algorithm is secure that we can't really use on a language like Python. There are some issues with the character encoding in Python. So if you're sending like a stream of bytes, some things might not be encoded as you expect, and that might cause your encryption to work differently. And then finally, Python handles its own memory. So the destruction of keys when you're doing encryption might not happen exactly as you would want it to. They might stick around for a little bit longer than you would want. So those are a little bit of the drawbacks and some of the reasons why it's good to use Python for cryptography. The installation of the cryptography module is pretty easy. I thought I would go ahead and put it here, but you can use whatever package manager you prefer, and you just install cryptography. And I want to go over some of the terms that we've been using a little bit today and that we'll continue to use. Encryption, as you might guess, is encoding a particular message using a key and an encryption algorithm. And as we talked about earlier, it's important that the secrecy of your system should rely upon the secrecy of the key and not the algorithm. So if the secrecy of the system just depends on no one knowing exactly how I'm doing my substitution, that's not very secure. Key derivation is a process for creating suitable keys for use in encryption, so it's a very important part of the process. Plain text is not necessarily text, it's just the original unencrypted input in its natural form. So it could be a stream of different bits, it could be a text file, it could be a bitmap or an image. The ciphertext is that input that's been transformed or encrypted in some way. And again, it doesn't actually have to be text. So this is just like a really simple graphic to show you this is a plain text, it becomes a ciphertext, and then using our encryption key, we can get the plain text again. A message digest essentially is a method of creating a hash code to check if the original is unmodified. So you cannot use this to decrypt the original method, but you can like apply this hash code and then compare two different messages. So for example, if I had like this really long message and I wanted to check if it's the same as this other one, I could get the hash code for both of them and then compare those. And that's less memory potentially than looking at the fully encrypted version. But I can't go back from there. I can't use that to get to the original decrypted message. So it's kind of like a fingerprint symbol or like a signature. Yeah, so in that case, you use this hash function to get your encoded text. And cipher, so this is an example of plain text and ciphertext. So on the left, you've got your plain text, and then on the right, you've got your ciphertext, which is the encoded version. Great, so now I want to talk a little bit about ciphers. We'll talk about some pretty basic ones and how they work. We've already gone over some historical examples, like for example, the Caesar cipher is a very popularly mentioned one. And we've also talked a little bit about how you could break something like this by looking at letter frequencies. So a popular one is the Zora cipher, which is converting plain text to ciphertext by using the Zora process. So I thought I would, show you how this might work in Python. So we'll go ahead and run it. But basically, you can see that it's just like ORing these two characters, X and Y, right here. And let me make sure there are no questions. Awesome. Cool. Yeah, so that's the code right there. And I will go ahead and run it. And we've got a problem. It's complaining about my indenting. Okay. I see. Cool. I'm going to add parentheses on my print lines. Problem with doing a live demo. And this. Okay, and then I think I might be using the wrong version of Python here. Great, okay. So the plain text here is just the Zora procedure, and you can see that the ciphertext looks something like this. Let's do it one more time. Yeah, so it looks the same way because it's using the same substitution, and that's just a pretty basic way that you could create a simple cipher and decode based on that. Awesome. Cool. And so we talked about Caesar ciphers before, but it's a substitution cipher that just works by replacing each letter with another that's a fixed number of letters down the alphabet. And I thought I would show that one. Cool. So the original in this case is ciphering is fun, and you can see that the cipher looks something like this. And let's go ahead and change the shift here. Shift 4 characters down. You can see that that modifies the text here. And yeah, we're just using a little bit of a shift down the alphabet to do that. Cool. So those are two pretty basic ciphers. Yeah, and then I also wanted to say that if you want to use PICrypto, you can install it this way, but it's not recommended that you do so because it's not maintained anymore as of a few years ago. But you can use PICrypto to encrypt files. You probably can in cryptography by this point, but PICrypto has a method of doing it that still works. And basically, passwords are generated using a hash algorithm that's then used to encrypt files. So I'm not going to run this one, but we will kind of look like at what it might do. So essentially, you can see here that you're getting a random number passing in 16 bytes here, and then you're accessing something called the advanced encryption standard, and you're passing in that random number generator and the key, and then that gives you your cipher, which you can use to encrypt the file that's being sent in. So we talked about the advanced encryption standard. You can see that most libraries like this one have it built in so that you can just pass in exactly how many bits you want to use and your random number generator. It looks like they're passing in a key as well, and then get the cipher. And then if you go in the documentation page and you look at message digests, there's a little warning there that says this is a hazardous materials module. You should only use it if you're 100% sure that you know what you're doing, because it's full of landmines, dragons, and dinosaurs with laser guns. So again, I'm not giving you cryptography advice. If you're going to actually use any of this to encrypt secure systems, you should make sure you're following regulations and everything's well tested. And it's really probably better to just kind of play around with this stuff and then use the accepted algorithms or systems to do encryption if you're storing secure data. Cool. So we talked about message digests. This is in the cryptography library. It's importing, let's see, hashes in a default backend, and then it's passing in some text, and this is the hash that you might receive as a result of that. So now let's talk about key derivation functions. Basically, these are a way of essentially passing in a key and then obtaining a secure value from that. So a key derivation function is a pretty critical component of most cryptographic systems. Its goal is to take a source of some initial key material, which usually has some amount of randomness, but maybe is not distributed uniformly, or maybe like you're worried the attacker has some partial knowledge about the key, and then make it a little bit stronger. So it's essentially a function that it's a function that takes input that's random in some sense and then produces output that's random in a cryptographically secure sense. So this is useful in a few different kinds of situations. For example, if, like I said before, if your output is not uniformly distributed, if you have a random number generator that refreshes itself periodically from values that are obtained by measuring random events, like for example, packet timing or mouse movements, those are also not uniforms. You could take those as random input and then use your KDF to sort of stabilize that. And yeah, that's essentially what a key derivation function does. So usually it takes a password assault and some kind of cost factor, complexity factor, and then inputs them to generate some kind of password hash. And the purpose is to make any guessing of that password by an attacker who's got some kind of hash file very expensive, prohibitively expensive. Cool, and this is how that looks in the cryptography library. So you import this hashes, and then you import this, and I'm gonna show you a little bit about how it works. I'm not gonna run it, but essentially you're passing in the particular kind of algorithm you wanna use and the length, and how many iterations you want to do. And then let's say you pass in migrate password, and it'll give you some output. Cool, so I wanna talk about some common breaches of cryptography because this is something that people are often interested in. Not encrypting all of the things that you should be is definitely a big one. Choosing the wrong flavor. So there are a lot of different decisions to be made here. You don't just like choose one method of encryption and then run with that. You have to choose like your algorithm and then often some key derivation functions and then the key that you're going to use. To do that, maybe you have to pick a source of randomness. There are a lot of different levels to it. So if you're not using the right flavor for your purposes, I'll talk a little bit more about what that means. using cloud storage without pre-encrypting, so assuming that like AWS will take care of all of this for you, is also a common method or a common source of breaches. And then using a poor random number generator, which is kind of the source of those attacks we were talking about earlier with the weakness in the dual PRNG algorithm. Yeah, so when it comes to cloud encryption, AWS refers to this model as shared responsibility. So the idea is that AWS has responsibility, I think it says security of the cloud. So inside the cloud, responsible for the security of like database operations, storage, and computations. But you are responsible for security that's within the cloud. So encrypting your customer data, for example, your firewall configuration, server-side encryption, network traffic protection, that all falls upon the responsibility of the customer. So that can be a common source of breaches if people are just kind of like passing their data to AWS and assuming it'll encrypt it and deal with it. And then, yeah, I talked about flavors of some of these things. So when it comes to advanced encryption standards, this is a question someone asked on Stack Overflow. They were asking about different methods of AES, and this person is explaining when to use different ones. So these are some of the different flavors or modes that you can use in AES. And this says that ECB should be used if you're encrypting more than one block of data with the same key. So if you want to use the same key for several different blocks. These methods are better if you only need encryption and you don't need to decrypt it, which can save you some memory space. If it's really important to you to have speed, then you can use something like CTR. XTS is the most common if you're encoding something that's randomly accessible, like a hard disk or RAM. And then at OCB, it says, is by far the best mode as it allows encryption and authentication in a single pass. But it seems like access might be restricted to that because of some of the patents that are out there. So basically, I'm showing you this to say that it's not just like, oh, I'll use the advanced encryption standard and then I'm good to go. There are a lot of other things that need to be configured according to your purposes. Cool. So if this is something that you're interested in, I thought I would suggest some starter projects. You might try making your own file encryptor or coming up with your own cipher. There are a lot of cryptography challenges out there, both for like decrypting ciphers and coming up with your own. So you can go and seek some of those out. Those can be pretty fun. And then I also said that you can contribute to the open source cryptography module. So I thought I would include some screenshots of some of the things that are available right now to be worked on. This one says, allow key material to use byte array instead of bytes. So this person is reporting that currently the library requires key material to be immutable bytes types for most functions, and he thinks it'd be useful for it to be the byte array type. So yeah, that's something that would fix this user's design case and is something you could do in order to improve the cryptography module. This one is a request for a streaming API so that you could call encrypt in a loop. That was submitted a few years ago, it looks like. And then, yeah, so those are the things that are out there. If you're interested in contributing to the cryptography module, you can also go and search by good first issue. And those are typically things that are intended to be a good introduction to the module and contributing to it and how that works. So I highly recommend that you do that if you're interested. Well, so let's wrap up a little bit. In summary, cryptography is something that's very important to us every single day. It's difficult to achieve in a way that is cheap, and there's lots of work to be done out there. So we'd love if you could help with that. So yeah, if you have something to say, feel free to tweet at me or message me and ask me any questions. And thank you all for, if you're live, waking up this weekend to watch this, and then if you're watching this later on, watching it in the future, whenever that may be. And now I'm going to look at the chat room. Oops. I think I lost my window there. So let me go ahead and put that up in. And I believe the questions link is great. yeah, so if you have questions, you can go to remote. Cool. So I don't see any questions here. So if you have any, feel free to tweet at me or whatever. And I see some people are saying that they can't see the demo. So let me go ahead and share my entire screen if I can do that. Oh, hello. Cool. So I will go ahead and show a couple of those demos again. So if you want to see the Zor one, basically the ciphertext looks something like this, and then the plain text that was encrypted said Zor procedure. And then for the Caesar one, I'll do that one really quick. Ciphering is fun, and the cipher said this. And then let me pull up the code that I used. So for the Caesar one, it's applying the shift to a particular kind of alphabet. And then for the Zor one, it's just ORing these two characters in the middle and then joining them all together and using that to encrypt. So sorry about that. Didn't realize I was only sharing a particular application window, but thanks for pointing that out. And yeah, so if you have any questions, feel free to tweet at me or ask me any questions. And yeah, thanks everybody.